Okay, good afternoon, everybody. It's 12 o'clock, so we'll go ahead and get started. The only reminder I have for you today is that next week is lab number 2, so make sure you do get the pre-lab ready and you're good to go there. Next week's lab is all about sound in tubes, so the things we've been talking about this week you'll see in the lab next week, so hopefully that timing is pretty good. So, we're going to switch topics a little bit today. And we're going to talk about interference some more. And we know that interference is what happens when we combine 2 or more waves. So we're going to take our setup. Here's the picture I'm going to draw on. This is not exactly the real setup. What we have in our actual setup is we have one speaker right here. This speaker is emitting a sound wave. It looks like this. Then we have another speaker that's placed a little bit in front of it. This one is also emitting a sound wave. And then we have a person who's standing in front of both those speakers, and this person here is listening. So really everything is all in a line, everything is in a row, but it's hard to make our diagrams nice if I draw them that way because we want to be able to see the details. So just for image's sake, I'm going to split them, but know in the back of your mind that they're really on top of each other. So we're going to start by saying we have 2 sources, and this, we're mostly going to talk about sound. So we have 2 sources of sound, 2 speakers. They emit wave in phase. So when we say in phase, we mean the sound comes out at the same point in the cycle. So the sound waves might both be on a crest or both be on a trough. Whichever it is, they're identical for both of them. So we'll say, example, both on crests. So sound waves are coming out, they both emit in the same way, and what we're going to ask is the person who is standing here listening to those sound waves, her ear is right here at this dashed line. What does that person going to hear? What do you think the kind of interference is for the person right here? Constructive. So this wave is on a crest, this wave is on a crest. They line up crest to crest. That's constructive interference, just like we saw in our waves earlier. So our waves meet crest to crest. When 2 waves meet crest to crest, they add up, they get bigger. This is constructive interference. In terms of sound, when we have constructive interference, that would be a loud sound. So when a sound wave gets bigger, it gets louder. So let's layer in a mathematical approach for this, because every time we do a problem, we're not going to draw the sound waves and look at what happens where the person is listening. Sorry, I just got to tickle my throat. So we're going to make a couple of new definitions. People do tend to get tangled in these definitions, so make sure you're not one of those people. This is speaker 2. We're going to say that the distance between the person and speaker 2 is D2. And the distance between the person and speaker 1 is D1. Okay? You're probably laughing at me when I say people get confused about that. People get confused about that all the time. They get it wrong on assignments and tests. So you got speakers 1 and 2, D1 and D2 are the distance from the person who's listening to the speaker. So we'll write that down. D1 is the distance between the person and speaker 1. And D2 is the distance between the person and speaker 2. Okay, the next definition we'll put in here is what we're going to call path difference. So path difference has a symbol of delta D, and it's the difference between these two distances. We don't care which one's bigger and which one's smaller. So to find a path difference, we'll do the absolute value of D2 minus D1. Okay, so these three things are the three definitions you have to know about this kind of a problem, a path difference problem. If you can keep these things straight, you can do any problem I throw at you, as long as you remember what these definitions are. So let's put path difference on our picture, and we'll see if we can find conditions to give us constructive interference. So this is D2. If I take away D1, I get this distance right here. So this distance is delta D. In terms of the wave up here, I see that my delta D is equal to 1 wavelength. So for this picture we've drawn, delta D equals 1 wavelength. So delta D equals lambda, and what we're getting here is loud sound or constructive interference. Okay, any questions here? So they come out the same way. If the two distances are off by 1 wavelength, they'll still meet up crest to crest. We basically just shifted it a wavelength. So are we good to hear? Yep.
So is D2 minus D1 always lambda?
That's a good question. Why don't we keep working on that for a little while? Okay, so that's a great question. So where we're going is exactly related to that question. Let's get a relationship between delta D and lambda and see what that tells us about the type of interference and the type of sound. So the next thing I'm going to do is I'm going to take my speaker 1, I'm going to move it a bit, let's find the new delta D, let's find the new kind of interference. So I slide my speaker down to right here. Let's ask with what we see first. A person that has got their ear right here, the sound is still lining up crest to crest. This is still constructive interference or loud sound. So we've got the same result here. So what kind of interference? We've still got crest to crest. I'll use a little bit of shorthand. I'll say CON for constructive, and then that means loud sound. In terms of our path length differences, so D1 is my distance from speaker 1 to my person. This is D1. That's a bit small in this picture. D2 is my person to speaker 2. That one didn't change. Delta D is my difference between those two things. So my path length difference, delta D, is D2, take away D1. That's the distance from here to here. This is delta D. In terms of a wavelength, we've got one full wavelength, and then we've got another full wavelength. This time it's equal to 2 times lambda. So if your waves are coming out in the same way, if they're in phase, anytime you shift one of your speakers by a whole wavelength, they'll stay in phase. They'll still meet up crest to crest where the person is standing and listening. So our general conclusion is that if two sources emit sound in phase, so in phase is really important, we will get constructive interference, which corresponds to loud sound if we're talking about speakers. Anytime our path difference delta D, anytime that is an integer multiple of lambda, where n is 0, 1, 2, 3, and so on. Okay, so that's our general condition for constructive interference when we have in-phase sources. Questions? Yep.
Does it have to be from crest to crest or like from trough to trough also?
Yeah, it could also be trough to trough. It just means they meet up at the same point
like
in the
any
cycle.
point and its adjacent point?
Yeah, the same point in the phase for the other one. Yeah. So they have to meet at the same point in the cycle. Okay, so that's when they meet up crest to crest. You might start to wonder, well, what if they didn't meet up crest to crest? That's the bit we'll look at next week. Yep.
What if it is not exactly crest to crest? Like?
Okay, so we're going to do not crest to crest next. So we've got the same setup. The only thing is I've shifted my speaker 1 a little bit, so now they're meeting up crest to trough. So the waves meet crest to trough. What kind of interference is this one?
Destructive.
This one's destructive. That means those two waves at that point cancel out. That means there will either be no sound or very quiet sound. Sometimes I'll say quiet instead of no sound or silence, just because in the real world you get a little bit of echoing effects and stuff. Okay, so we'll just say quiet sound. So let's apply the process. D1 is from speaker 1 to our person. D2 is from speaker 2 to our person. Our path length difference, delta D, is the difference between D2 and D1. We'll look at that difference on our picture. And our difference now is a half of a wavelength. This is our delta D this time. This is lambda over 2. So this time delta D is lambda over 2, and we get destructive interference or quiet sound. If I took this speaker and I shifted it down one more wavelength, I would get delta D equals 3 times lambda over 2, and it would still meet crest to trough. Could shift it some more and it would be 5 lambda over 2. So our general relationship for speakers or sound sources that are in phase, we will get destructive interference, which corresponds to quiet sound, if our path length difference, delta D, is n times lambda over 2, where n is 1, 3, 5, and so on. So basically, if your sources are in phase, if they meet up on an integer multiple of the wavelength, that's going to be constructive. If they're shifted by half a wavelength, so they're off by some half, that's going to be your destructive. Okay, so that's how we get them to meet crest to crest or crest to trough. Questions? Yep.
When will the sources be considered out of phase?
So out of phase, we are coming to next. It's like you've all read ahead and you know what's coming. First, I want to circle back to your question a little bit. So I looked at 2 cases. I looked at exactly crest to crest and exactly trough to trough. If you're wondering if there are in-between cases, yes, there absolutely are. But no, we're not going to talk about those. They're a little bit beyond what we want to get into. So in the real world, yes, that exists, but we're just going to look at these kind of 2 perfect cases. Okay, so let's do our out of phase sources next. So let's have our 2 speakers emitting sound out of phase. Out of phase means in opposite ways. So for example, one on a crest and the other on a trough. Where this might have happened to you in your lives, if you have a stereo system at home and you hook up external speakers, there are specific places that the 2 speaker wires have to go into the stereo. If you put them in backwards, you're hooking them up out of phase and you won't get good sound out of your speakers, right? So if you're hooking up your stereo system and the sound doesn't work and you Google, why isn't my stereo working? Your first hit will be, did you put the wires in backwards? Okay, so you switch the wires and they're in phase and it all works. So that's somewhere you might see that in your life. Okay, let's do the process again. So here are my 2 speakers. They're emitting sound. Notice that they're out of phase now. They come out different ways. Here's our person listening to the tunes. What does this person hear? The 2 sounds are meeting up crest to crest. If they meet up crest to crest, that's constructive. If it's constructive interference, that means loud sound. Okay, so there's our method. D1 is from our person to speaker 1. D2 is our person to speaker 2. Let's find what our path difference is. Path difference is D2, take away D1. So from here to here. When we look at our picture, we see that that path difference is a half of a wavelength. So if our speakers start out of phase, one is on a crest, one is at a trough, the way to get them to line back up is to shift one of them by some half of a wavelength. So that's how you're going to get them back in line. So when you shift one by a half of a wavelength. So if we've got our two sources, which are out of phase, so they start in opposite ways, we will get constructive interference, which means loud sound, if our path length difference, delta D, is n times lambda over 2, where n is an odd integer. So what you might notice here, to get constructive interference for out of phase sources, that's the same condition as destructive for in phase sources, okay? Because we've got to have the same behavior, so the conditions just have to flip here. Okay, so that's constructive for out of phase. The last one we'll look at is destructive for out of phase. You might have a guess where this one is going to end up. Okay. And then I've got one slide that puts this all together really nicely. I've got everything all laid out with the equations on it. So I've got my out of phase sources, I've got my person listening, one wave is at a crest, one wave is at a trough, so our sound waves are meeting crest to trough. Crest to trough is destructive interference, which is our quiet sound or no sound, okay, because it meets crest to trough. D1 is our person to speaker 1, D2 is our person to speaker 2, delta D is the difference between those two lengths. So delta D is D2, take away D1 equals. Look at that on our picture. There's our delta D. We see that that's equal to a full wavelength. Delta D equals a wavelength. So if they start out of phase, anytime you shift one of them by a whole cycle, they'll still be out of phase. So our general conclusion is if our sources are out of phase, so they start in opposite ways, we will get our destructive interference, and destructive corresponds to quiet sound, if our path length difference delta D is an integer multiple of lambda. Okay, so did I end up addressing all of the questions? Okay, super. So I'll just put up that next slide that looks so nice. We'll bring all your notes together. So our constructive interference happens when waves meet crest to crest or trough to trough at the same point in the cycle. Destructive interference happens when waves meet, I'm sorry, you can't take pictures of anything that's up here. We can't do any kind of recording. And I post all this stuff on Brightspace. Destructive interference when waves meet crest to trough, two opposite points in the cycle. If our waves start in phase, we get constructive if delta D is n lambda. We get destructive if it's lambda over 2. If the waves start out of phase, then our conditions flip. Okay, so there's our results. We're going to get into how to put this into practice, and we'll see the physical, we'll do an actual physical example of what this means beyond hooking up your speakers. Does anybody have any questions about this? So another application, before we get into, kind of problems where we do numbers and all that stuff, is, I guess everybody has headphones or earbuds. Okay, everybody has those these days, right? How many people have noise canceling headphones? Usually that's kind of, some people have noise canceling. Everybody's heard of noise canceling headphones? So they work on this principle, okay? So what happens is you put on the headphones. Somewhere on the outside of your headphone, there's a little tiny microphone. That microphone will record all of the noise around you. So say you're in the UC and you're doing your studying. You put your headphones on because you'd like it to be a little quiet. It will record all of the sound around you in the UC. then it's gonna play back that sound, but it's gonna play it back 180 degrees out of phase. It's gonna shift it by a half of a wavelength. It's gonna play it back. It will play back against the ambient sound, and those sound waves will cancel. So noise canceling headphones, they don't block out the sound like earplugs do. They actually cancel the sound wave by playing it back out of phase. So I think that's kind of an interesting application of this stuff. Questions? Okay. All right, let's get into some examples. So we'll start with some linear stuff, and then we'll go into some two-dimensional stuff and three-dimensional stuff. So you're standing in between two speakers. They're playing a tone of 172 hertz, so that's the frequency. It says that the speakers are in phase, and the speed of sound in air is 344 meters per second. So we want to find a few things. We'll start small here with our problem. First of all, part A, what is the wavelength of sound? We have the frequency and the speed. The wavelength is going to be pretty easy to find. So our frequency is 172 hertz. Speed of sound V is 344 meters per second. Part A, we'd like to find the wavelength. V equals F times lambda. So lambda is equal to V divided by F. 344 meters per second divided by 172 hertz gives us 2 meters. That's often the part A of these problems. You're given a frequency, you have to find the wavelength. Once in a while you might be given the temperature. You'd have to use that temperature equation to find the speed of sound. Like that would be one way to shake this up a little. Part B, and lots of times in a test question, part B is not going to be there. That's sort of an implied question. You'd have to calculate it anyway. Sometimes I'll ask for it, sometimes I won't. So what is the path difference where you're standing? So to find the path difference, we know delta D is D2 minus D1. We need to find D1 and D2. Let's label our speakers 1 and 2. I'm going to label this speaker, speaker 1. I'm going to label this speaker, speaker 2. If you do it differently, if you label these 1 and 2, it doesn't matter. You'll get the same answer. So D1 is from our person to speaker 1. Let's put that on our picture. And the picture shows us that that's 4 meters. So D1 is 4 meters. D2 is our person to speaker 2. Our picture doesn't show us D2, and it's problems like this. You know, I said that people get confused with this stuff all the time. A lot of times there's a temptation to say D1 equals 4 and D2 equals 12 because that's a number given in the picture. So make sure you don't fall into that trap. D2 is this distance, so that's going to be 12 meters, subtract 4 meters. So D2 is 8 meters. So for part B, our path difference delta D is D2, subtract D1. 8 meters, subtract 4 meters, equals 4 meters. Okay, any questions? And then a typical part is, do you hear loud sound or do you hear quiet sound? So what does it sound like where you're standing? So here's where we have to look at our conditions for interference. I would suggest to you that as you're doing your problems, have this set of equations, this set of conditions, on a sticky note next to your paper. So put it right there next to you where you can look at it. It'll help you know where you're supposed to go with this. So we're told that our speakers are in phase. So right off the bat, we know that these are the equations we're looking at. We don't have to think about the equations for out of phase sources. So what we know is delta D, and we know lambda. So we have to ask, which of these two equations do our delta D and lambda satisfy together? Sometimes you're gonna be able to tell just by looking at the numbers. So if that describes you, that's fine. It's okay to just look at it and you can tell. You do also have to be able to put some words to it. So in general, what we'll wanna do is follow the process where we'll say that since our speakers are in phase, in order to have loud sound, it has to be constructive interference. That means that delta D divided by lambda would be equal to N. Okay, so all I did up here was I took this equation and I divided both sides by lambda. Delta D over lambda equals N. If I had quiet sound, delta D over lambda equals N divided by 2 equals 1 over 2, 3 over 2, 5 over 2, and so on. Okay, so this is what I have to test. What is delta D divided by lambda? And then I'm going to have my answer. Okay, I don't think I can write any smaller, so I have another sheet of paper. It's still down here. So for our problem, delta D divided by lambda, delta D is 4 meters, lambda is 2 meters, so delta D divided by lambda is equal to 2, okay, exactly 2. In these problems, it is important to put down your statement with your reasoning, to throw a few words in this sort of question. So a way you might summarize this would be, this matches the condition for loud sound for in-phase sources i.e. delta D equals N lambda, N equals 0, 1, 2, with N equals 2. Okay, so you say what the condition is, you say what your setup is, loud sound in phase sources, and you say what your results were. Okay, so that's how you show it's loud sound. Yep.
For something like this, will we be able to say that we can see that it's 2 full wavelengths and we know that it's coming out of phase? The distance is equal to 2 full wavelengths, so we can just infer that they would be, since they're in phase.
So they have to stay in phase?
Yeah.
Yeah, it would be okay so long as you put in a statement supporting that. Yeah. And it would have to be clear, right? Yeah, you can't just make a wild guess and hope you're right. Yeah. Okay, so that's our first example. For a homework question that shouldn't be too tricky, do this problem again, but act as though the sources are out of phase. Okay, any other questions? No. So for our next one, we're going to take this geometry here and we're going to build on it when we go to two-dimensional waves. So we'll do this problem here as it is now, and then we'll do more on this in a little bit. Maybe today, maybe next time. So two speakers are separated by 12 meters, and you stand next to one of the speakers. When it says next to, it essentially means right next to it, no distance between you and the speakers, like no separation there. The speakers are playing a tone in phase of 172 hertz, that's your frequency. Speed of sound is 344. We're going to do that question again that we did last time. Okay, what's the path difference? Do you hear loud sound or quiet sound? So, what is the path difference? So we need our two values of D. I'm going to label my speakers, speaker 1 and speaker 2. Your ear is right up against speaker 1, so D1 equals 0 meters. Okay. You're 12 meters away from speaker 2. We'll label D2 in the picture. So then your path difference is the difference between those two things. So part A, the path difference is 12 meters. Part B, do you hear a loud sound or a quiet sound? So we're going to use our same approach as last time. Our sources are in phase. So we know that these are the conditions we're looking at. We want to look at delta D divided by lambda. Is it an integer or is it a half integer? So part B, delta D equals 12 meters. Lambda is V over F. We did this calculation on the previous page. That's 2 meters. So delta D divided by lambda is 12 meters divided by 2 meters equals even number 6. So our conclusion is that this matches condition for loud sound delta D equals n lambda, 1, 0, 1, 2, so on, for in-phase sources with n equals 6. So the person will hear loud sound. Any questions? So when you have your speakers all in a row like this, the problems are basically the same, right? Label D1, D2. One way to shake it up, it could be I tell you you hear loud sound. Then you might have to figure out were they in phase or out of phase. Like that would be one little twist I could throw in there. So if I told you it was loud sound, you would know you had to look at the top two conditions. And that should be able to tell you in phase or out of phase, so that's sort of a twist. I could tell you if it was in and out of phase. I could tell you it hears loud sound. I could give you D2 and ask you to find D1. You know, just so I could give you different bits of the problem and ask you to find different pieces. Yeah. Okay. Questions? Yep.
Will these conditions be written in the formula sheet, or we have to learn it by heart?
I'll give you a formula sheet. However, I won't put, in phase and out of phase or loud and quiet there, so I'll just put the equations like that there, and you have to know what they apply to. Okay, so that's when we have our speakers all in a line, all in a row. So those you might call one-dimensional waves. We also, of course, don't only ever have one-dimensional waves. We have 2D waves and 3D waves. So when we have 2D waves, like water waves on a pond, or three-dimensional waves, like light waves and sound waves, we get exactly the same behavior. Whenever the two waves meet crest to crest or trough to trough, we get constructive interference. The wave gets bigger, crest to crest or trough to trough. If they meet crest to trough, if they meet at opposite points, the wave gets smaller. So if you think about all those conditions, you get exactly the same conditions for interference, okay, with your path differences. So I'm going to show you a picture from a video.
Where we can see this with water waves. I have two sources of ripples, which are basically like the two slits. When I create ripples with a single source, they travel out with circular wavefronts. Nothing particularly surprising there. But if I add a second source of ripples, then we start getting an interesting pattern. This pattern is created by the ripples from the two sources interacting with each other. Where they meet up peaks with peaks and troughs with troughs, the amplitude of the wave is increased. That's what we call constructive interference. But if the peak from one wave meets up with the trough from the other, then we get destructive interference, and there's basically no wave there. And this is exactly what was happening with the light.
Okay, so he goes on to talk about light interference. If you're interested in that, you would see it in another more senior physics course. So that's what happens with water waves. So those are two-dimensional waves. We can also think about three-dimensional waves. So this room has 2 speakers, so we've got 2 sound sources. I'm going to play a sound wave, and you should be able to find places of constructive and destructive interference. So I'll hit play. Okay, that's not as painful as the higher tones. So I hope everybody can hear it. Now what you have to do is move your head, just lean back and forth a little bit, by about a half a meter. So when I'm right here, it's really loud. And when I'm right here, it's pretty quiet. You can get the same effect by standing up and down because the sound is a 3-dimensional wave throughout all the room. So those ripples he had on the pond showing the interference, you're sitting in that pattern right now. If you put your head where it's quiet, you've got one sound wave at a crest and one sound wave at a trough, and it's flattening out. It's not totally quiet because the room's got horrible walls and sound is bouncing around everywhere. And if you're at a place where the sound is loud, you've got one wave at a crest and the other wave at a crest, and the sound wave is getting bigger. Okay, so you're sitting in that interference pattern right now. Okay, so let's go back to here. When we draw those waves, we draw them and we just put circles to show the crests of the waves. So sometimes it's harder to draw them in 2 dimensions. So we use a crest or a circle just to show the crests. So if we have 2D and 3D waves, we have exactly the same results. If your path difference is off by an integer multiple of the wavelength, we get constructive, if they're in phase. If it's off by a half wavelength, we get destructive. You can have your sources out of phase if your speakers are hooked up backwards, and then the conditions are flipped. So it's exactly the same results. We can look at a couple of those on this diagram if you want to. The diagram is a bit busy. I got it from your textbook. So I've got 2 sources of sound. So that's these little stars in the middle. I'm going to label them 1 and 2. And let's ask what kind of sound or what kind of interference do we have right here at point A. So if we want to interpret the diagram, all of these circles show the crests of the wave coming from the source. So all these lines are crests. In between any 2 crests would be a trough. So the exact middle between 2 lines would be the troughs. If we look at my 2 waves, I see that right here where I picked point A, I've got a blue line crossing with a green line. That means a blue crest is meeting a green crest. So at point A, they are crest to crest, which means constructive. We can also do our analysis just like we did with the 1-dimensional waves. We can look at D1 and D2. So D1 is our distance from our first wave, our first source. So there's D1. Let's think about D1 in terms of a wavelength. The distance between any 2 crests as a wave goes up and down, the distance between any 2 crests is a wavelength. So I go from the source to a crest, that's lambda, to another crest, that's 2 lambda. Okay, so this distance D1 from source 1 to my point A is 2 times a wavelength. From my source 2 to my point A, I can draw that in my picture. So there's D2. I can find D2 in terms of wavelengths. So I go from my source to my first crest, that's 1 lambda. To my second crest, that's 2 lambdas. To my third crest, that's 3 lambdas. So D2 is 3 times lambda. So then to do our analysis, we find delta D. Delta D is equal to D2 minus D1. 3 lambda subtract 2 lambda equals lambda. And it is loud sound. Okay, so these 2 sources emit waves in phase in the same way. They both come out on a crest. I see that they meet up crest to crest, so I know it has to be constructive. And when I do my analysis of the path length difference, I see that I'm getting the same results that I did for my waves when they were all in a line. So delta D equals lambda, and we get our loud sound. Okay, any questions?
Are they in phase?
Yep, these are in phase because they both emit on a crest. So I'll give you 2 points to look at for homework, and I'll post those answers. So for point B, I'll put that right here. So here's point B. So it's in the middle between two green crests, and it's in the middle between two blue crests. So there's our point B. And for point C, I'll put down right here. Point C is on top of a green crest, and it's in between two blue crests. Okay, so B and C will be for homework. And I will post those answers for you to have a look at. But maybe you know the answers already. Okay, questions? So now we're going to go back to our example, the one I said we were going to build on a little bit. So that example that we did a few moments ago, we had two speakers separated by 12 meters. You were standing up against one speaker. We found the path difference was 12 meters. We saw that delta D divided by lambda was 6, and we concluded that you would hear loud sound. So that's what we did a minute ago. We're going to take that same setup and just change it a little bit. So in my question, I noticed that I did make one typo, so if you've downloaded the notes, you can make this fix. So our two speakers are separated by 12. The text says you stand 2.2 meters in front of one speaker, and the diagram says 2. That should say 2.2. Okay. So that fixes our typo. The speakers are playing that same tone, 172 hertz. The speed of sound in air is 343. What is the path difference where you're standing? Then to tie it back to our previous problem, I'm going to ask you to compare it to the path difference from before. And then do you hear loud sound or quiet sound? Justify your answer by relating the path difference to the wavelength. Okay, so what is the path difference? Let's get started on that problem. I'm going to label the speakers 1 and 2. Again, this is a problem where students get into trouble with the path differences. Some students will say that D1 is 2.2 and D2 is equal to 12 because those are two numbers given on the picture. This is why you always have to draw those path differences, and you always have to make sure you know what they are. So D1 is our distance to speaker 1 from our person. That is in fact 2.2 meters. D2 is our person to speaker 2. That's from here to here. That is not 12 meters. We have to figure out D2 from the geometry. We can see that that's the hypotenuse of a right angle triangle, so we can use Pythagorean theorem to figure out what D2 is. So D2 is going to be the square root of 12 meters squared plus 2.2 meters squared gives us 12.2 meters. What is the path difference? So path difference, delta D, maybe I'll write that down here where I've got a little more space. Delta D is equal to D2, subtract D1, 12.2 meters, subtract 2.2 meters to get 10.0 meters. So now our comparison question, did this get bigger or did this get smaller? Let's see how much of this I can get up at the same time. So delta D is 10 meters when you've moved away. When you're standing right in front of it, I can't put them both up on the same side. I need more space. When you're standing right in front of it, delta D was 12 meters. So when you're right up next to the speaker, That's when you have the maximum path difference. As you move away, your path difference gets smaller. Okay, so this is smaller, the path difference decreased. I'm stressing on this one a little bit because it will help you with your assignment question about Oscar and the speakers. So you've got one question on the assignment that's more or less based on this example. So I'm trying to put that in there to give you a hand when we get to there. Okay, do you hear loud or quiet? Justify your answer. So we'll compare our delta D and our lambda and we'll make our conclusions. So part B, delta D divided by lambda is going to be 10 meters. Maybe you remember from last time, maybe you calculated again. Delta lambda is V divided by F, 344 meters per second divided by 172 hertz, or 2 meters. Delta D divided by lambda is 10 divided by 2, or 5. Delta D equals 5 lambda, matches condition for in-phase sources for loud sound. With n equals 5. The other thing I'll point out here, again, just to try and give you a hint about that Oscar problem, where we were standing right up against the speaker, n was equal to 6. When we've walked away a bit, n equals 5, so that n value gets smaller as we walk outwards because the path difference decreases.
Doctor?
Yep.
In this question, what is this bigger or smaller than the path difference when you stood in front of the speaker?
Yep.
Which speaker does he mean? 1 or 2?
It's referring back to this problem.
So, is it 1?
Yeah, speaker 1. Yeah. Okay, the next problem has got us walking away from the speaker all the way out to when we find sound for the last time. We're not going to finish it in a couple of minutes, so we'll quit that here and we'll pick up that one on Monday. If you want to get a head start, you might see if you can do it, and you would do that one with the Oscar problem side by side.